bonds between O and H, and those are going to be pretty strong. But when we're talking about intermolecular forces, we're not talking about that internal stuff. We're talking about external stuff. In terms of how, this is the dotted lines we're talking about, where the forces that hold one molecule up close to its neighbors, how strong are they? And how do you figure that out from a Lewis structure? So that you can predict which ones have higher melting points than others, which ones have higher boiling points than others, which ones are going to have a high viscosity and which ones are going to be low. And making those kinds of predictions based on nothing more than a chemical formula, where you're given a formula like SF6, and you go through to the Lewis structure, you go through to your sigma and your pi and your resonance and your shapes, and then you get into predicting these properties. There's an awful lot of information you can pull out of a Lewis structure. And so we're still adding more to that list of things we can pull out from that. So to start off, there's different types of intermolecular forces that we'll talk about a little bit toward the end. But right here at the beginning, we're just going to talk about these forces in terms of strong or weak. And toward the end of class, we'll put names on what kinds give you strong and what kinds give you weak. But first of all, just defining the properties. The first observable physical property we're going to talk about is surface tension. Surface tension, defined here, is the cohesive force that causes liquids to adhere into droplets in resistance to gravity. Underline that. This liquid, whatever it is, forms a bigger droplet than the one to the side, correct? Whatever molecules you've got, for whatever reason, the ones on the left are piling up in resistance to gravity. These pile up better than those two. Now gravity would like to just squish them out flat, correct? But you've got forces of attraction between molecules that resist that and tend to hold on to each other and resist squishing. So comparatively, the one on the left or the one on the right, which one has the higher surface tension? The one on the left. And so which one has the stronger intermolecular forces? The one on the left. Because the ability to do that derives from the strength of attraction. If those attractions aren't very strong, then gravity's going to squish it. But if they are pretty strong, then they're able to pile up and accumulate. And I guess the epitome of really, really, really high surface tension would be like a crystal, a solid, where it's very regular, very defined, and not non-squishable. Does that make sense? The stronger the attractions are, the more resistant it is to gravity. So as a summary list over here, let's say this. Things that have strong intermolecular forces. If the intermolecular forces are strong, you will have high surface tension. Second property is viscosity. Definition of viscosity is resistance to flow. So we've got two liquids. We're trying to pour the two liquids. For lack of creativity, let's just call them A and B. They're both in beakers. We tip them up. Which one flows better? Apparently A. because it comes streaming out and the other does not. Which one has stronger viscosity? B. Because B isn't flowing very much, and viscosity is resistance to flow. The more because to flow, they have to let go of their neighbors and slide past each other. And if they've got strong intermolecular forces, they don't want to let go, and they don't want to slip past. They want to hold on and stay where they are. So things with strong intermolecular forces generally have high viscosity. Melting point. Melting is turning a solid into a liquid by applying heat. So if you've got a solid, you heat it up, you're trying to make it melt. If it doesn't melt, you heat it some more, and you keep making it hotter, 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 until you make the particles let go of each other and flow. For things with strong intermolecular forces, are they going to have high or low melting points? High. Because if they're attached very strongly, it's going to take a lot of energy to make them let go. So things with strong intermolecular forces generally have high melting points. Vapor pressure. By definition, this would be gas phase pressure generated by evaporation of a liquid or solid. Vapor pressure requires that there be a solid or liquid present, because it has to do with that transition. We're used to liquids evaporating like water. It's not that often you see solids evaporate, but if you're familiar with dry ice, then that's exactly what it is. Dry ice is called dry ice because it's different from regular ice, which I guess would be wet ice, because regular ice will melt and puddle up and dry ice doesn't. It doesn't melt and puddle up, therefore it's considered dry and so forth. But that would be evaporation of a solid. But the key words in here, it is gas phase pressure, but it's generated by conversion of another substance from liquid or solid to the gas. So if you're talking about, like, let's say oxygen in the air generates a certain pressure, but that's not vapor pressure. Because at normal conditions, all of the oxygen is already gas phase, correct? That is gas phase pressure, but that's not vapor pressure, because we don't have puddles of oxygen laying around the room from which that evaporates, right? It's a permanent gas at normal conditions. So oxygen gas will give you gas pressure, but it will not be vapor pressure. Key words in that definition is that it's generated by evaporation. There has to be a condensed phase there. So if that's our beaker, and all these little round things are our molecules, then at whatever temperature this is, as these little particles, it's liquid, they're able to flow, they're able to move around a little bit, and they'll slip and slide past each other. As some of them move left, and some move right, and some move up, and some move down occasionally, some will move up and pop free of that liquid, and that's evaporation. Evaporation is purely a surface process. Evaporation is movement of liquid or solid molecules away from the surface of that material. Evaporation is strictly a surface process. All those molecules that are in that beaker, only the ones on the top have the ability to escape. So only the ones on the top have the ability to evaporate. So evaporation is affected by surface area. And you knew that already, because if you have 100 milliliters of water in a beaker, or 100 milliliters of water out in a tray, which one evaporates away first? The tray, because there's more of them on the surface and there's more that are able to escape at any given time. It's a function of surface area. Volatile and non-volatile. Volatile, as a definition, means it evaporates easily. Volatile has the connotation of being unstable or reactive or sensitive or explosive. And that connotation to volatile comes out of organic chemistry, where everything is flammable and you don't want vapors because they will become flammable or an explosive, and they're hazardous that way. But strictly speaking, volatile just means it evaporates easy, which I guess means that water is volatile, because water will evaporate. You don't want to guess what non-volatile means? Yeah, it's not going to evaporate. It evaporates very little or none at all.
What is the example?
I'm sorry?
What is the example?
Example of non-volatile? Something like salt.
Okay.
The forces are so strong, it's crystalline, and no particles are going to escape. Things that have strong intermolecular forces are going to hold on to each other very tightly. If these particles have strong intermolecular forces, then they're holding on. And that means not very many are going to pop free. So things with strong intermolecular forces generally have low vapor pressure.
Is it like oil?
Yeah.
Oil.
Yeah. And things with strong intermolecular forces, are they going to be volatile or non-volatile? Non-volatile. Boiling point. Boiling point is the temperature required to convert liquid into vapor, liquid into gas. In other words, here's our beaker full of liquid. We're not satisfied with only the surface ones popping free. We want to make it faster, we heat it up. How hot does it have to get to come to a boil and start converting from liquid to gas en masse? Things that have strong forces, are they going to have high or low boiling points? Going to be high, because it's going to take a lot of energy to make them let go. If the forces between molecules are strong, it's going to take a lot of energy to overcome them, which means you're going to have to make it rather hot, rather high temperature, in order to force them to let go. All right, now normal boiling point. Put a little star by each of these. Boiling point and normal boiling point. And you've got this chart to illustrate the difference between these. What you've got on this chart is a plot of vapor pressure on the y-axis and temperature on the x-axis. And I guess let's just start with water. If you're looking at the line that you've got for water, If you're at 0 degrees, it's not evaporating much. But as you make it warmer, 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 the molecules move faster, they start to break loose, and it generates more pressure. And that's the pattern for everybody. The hotter you get it, the more motion you have, the more of them are going to break free. So this is a plot of vapor pressure, how much vapor pressure you get from each substance as a function of temperature. (760) on this axis. Now the units here are torr. And I guess this is the first time we've talked about pressure units. 1 atm is a very distinct line on this chart. 1 atm or 760 torr, that's the same thing. Think of that as a unit conversion. 1 atmosphere is the same as 760 torr. That's different pressure units. But 1 atmosphere is defined as normal atmospheric pressure. And before, this would have been back on the first couple of days of class, when we talked about temperature scales, Celsius, Fahrenheit, and Kelvin. One of the reference points I gave you was that the boiling point of water is 100 degrees Celsius. Well, actually, it's not. Because this entire curve is boiling point. Boiling point is not a point. Boiling point depends upon the applied pressure. Because when you've got your little beaker and you've got your water that you're trying to heat, there's air molecules above it, correct? And the more compact, more pressure you have applied to it, the more difficult it is for those liquid particles to escape. So you think of it as resistance. If the applied pressure is only 500 torr, then water's going to boil at about 85 or 90 Celsius. 85 or 90 Celsius. If the applied pressure is 1,000 torr, then the boiling point of water is going to be about 105 or 110 Celsius. Boiling point is a variable that depends upon applied pressure. But normally you're not at 500 or 1,000 torr. Normally you're at 760 torr, so normally water is going to boil at, ta-da, 100 degrees Celsius. 100 degrees Celsius. The normal boiling point of water is 100 degrees because normally you're operating at 1 atmosphere. But as far as actual boiling point, that's a variable. That's a function of the pressure. Now there's a lot of information you can get out of a chart like this. And that's some of it. We could read this as, what's the vapor pressure of such and so as a function of temperature? What's the vapor pressure of methyl alcohol at 75 degrees? 75 degrees, methyl alcohol, I don't know, about 1,100 torr, something like that. This isn't the best label graph ever, but it gives you an idea of where things would be. You can read it as vapor pressure as a function of temperature. You can read it as boiling temperature as a function of applied pressure. If you were asked, what is the boiling point of methyl alcohol at 50 degrees? Or at 500 torr? What's the boiling point of methyl alcohol at 500 torr? That'd be about 55 degrees. It's vapor pressure as a function of temperature, or it's boiling temperature as a function of pressure. Do you see how to read it both ways? And another way you can read it is as a measure of intermolecular forces. At whatever temperature you want to take, and for no particular reason, let's take 50 degrees. water evaporates this much, benzene evaporates this much, methyl alcohol evaporates this much, and diethyl ether that much. Which of those materials is the most volatile? Diethyl ether, because it evaporates the most, correct? Which of those four materials has the strongest intermolecular forces? Water, you know that because it evaporates least, correct? So you can also read this off comparatively over who's got stronger forces than who, based on what we've already summarized over there on the right about evaporation. Or if we want to look at a certain pressure, then diethyl ether would have a normal boiling point of about 40 degrees. Methyl alcohol would have a boiling point of about 70 degrees. Benzene at about 80 degrees, and water at 100. And so by looking at those boiling points, 40, 70, 80, and 100, higher boiling point means stronger intermolecular forces, correct? So you can make comparisons off this chart. Notice those lines never cross. Now they get so close down here that it's hard to resolve them, but that's just because it's a very compressed graph. But those lines are never going to cross, because regardless of temperatures and pressures you use, water's just inherently stronger. The attractions in the water are just inherently stronger, and it's going to be that way.
What does torr measure?
It's a pressure unit, just like atmospheres, only it's broken into smaller units. It used to be that with barometers for pressure, they used a column of liquid mercury, like a mercury thermometer, only they used it for pressure rather than temperature, because it's very dense and it would take a lot of pressure to make it move, and that way you wouldn't have to have a very big column to detect your pressure. And so they used millimeters of mercury as units, and then over time they renamed that unit to be torr. It was named after a guy named Torricelli, who did something important. I don't know why. Someday I'll have my own unit. If I have to make it up myself, it won't happen. Question about this. I'm never going to get my own element, so I might as well get my own unit. It's the next best thing. Question about how to read a graph like this. There's more to it than just temperature and pressure. You can read off comparative strengths of attraction for these substances. Do you see how to do that? All right. Looking at this graph, which of these four materials has the highest viscosity? Now that's kind of tricky because viscosity is nowhere on this chart, at least not explicitly on the chart. But we know that high viscosity goes with strong forces. And who did we? Water. Yeah, we already said that water's got the stronger forces, right? So you'd be perfectly justified in predicting that based on what you know about strengths, water being the strongest of the four, then it's probably going to have the highest viscosity too. Surface tension, who's got the highest surface tension? Apparently water. There's nothing explicitly on that chart about surface tension. But it does tell you strength of forces, and you've got over there your list of effects that come from strength of forces. Question about applying that to this kind of a chart. All right.
What's the normal boiling point?
Normal boiling point is the temperature it takes to make the liquid boil at exactly 1 atmosphere. It's the boiling point at 1 atmosphere of pressure. Next page starts off with 2 bulleted questions. Go ahead and work these.
Sorry, I'm having trouble with the connection. Please try again in a moment.
For a substance with strong forces, is it going to have high or low melting point, high or low boiling point, etc.? Things with strong intermolecular forces. Is melting point going to be high or low? Boiling point. Vapor pressure. Good. And surface tension. Good. Question about those patterns. Strong intermolecular forces means they hold on to each other very tightly, very rigidly, and they're not going to let go. Not without a fight, at least. Question on that. All right, next one, you've got 2 substances, you don't know who they are, but you've got experimental numbers on their boiling points. And you want to extrapolate from that to these other properties. Based on the boiling points for each of these, which one's going to have the higher vapor pressure? You're okay with B. It doesn't take as much heat to make it boil. That means it's probably evaporating enough on its own to be pretty close. Higher surface tension. Okay. If it's got the higher boiling point, it's more resistant to letting go, and it's going to hold on to each other more tightly, therefore higher surface tension. Question about these kinds of comparisons.
Can you explain why B is higher than pressure?
Because when you compare these 2 boiling points, this one is boiling at a lower temperature. That means you're more able to separate those molecules. And one aspect of separating the molecules is evaporation. So if it boils easier, then it evaporates easier.
So with a higher temperature, it doesn't boil?
This one, you have to get it to 30 degrees before it's going to boil. But that one will boil at only 20. So think of it like if you've got these 2 beakers, A and B, and let's just pick 25 degrees. For A, this one's not going to be boiling because its boiling point is 30 degrees. At 25 degrees, this one will not be boiling, but this one will. And so if B is already boiling and A is not, then you're separating the molecules of B when you're unable to separate the molecules of A. So higher boiling point is a reflection of stronger attractions. The higher that boiling point goes, the more tightly they're holding on. So next then is where we look at how to look at a Lewis structure and figure out strong or weak. And this is where we put names to these types of forces. And so this is kind of, this column thing here is kind of the thought process you need to go through in order to figure out strong or weak forces. And it all goes back to starting with the type of bonding. Is it ionic or covalent? How do you look at a chemical formula and tell if it's ionic or covalent? What do you look for? Ionic is going to be metals or ammonium with nonmetals, correct? Covalent will be entirely nonmetal. So the first thing you want to do is categorize the compound as ionic or covalent. Ionic compounds, or ionic bonding, gives you an ionic compound, which in turn gives you what's called ionic forces of attraction. And that's just the simple positive-negative attraction we talked about before when we defined ionic. And if it's ionic, then it has very strong forces. This listing over here, ionic, hydrogen bonding, dipole, and London, that is the order of strengths. Now we're going to go through how you assess who's got what, but that is already the order of strength. Ionic is stronger than hydrogen bonding, which is stronger than dipole, which is stronger than London. Ionic compounds have very strong forces, and that's why all ionic compounds are solids at room temperature. The forces are so strong that 25 degrees Celsius or whatever is not enough to make them melt, much less boil or evaporate. Very strong attractions because you've got completely developed charges. So if it's ionic, then I guess your forces is automatic. It's going to be ionic and it's going to be strong. Now if it's covalent, then we got to start thinking about shape. We need to look at covalent compounds and tell if they're polar or non-polar, because that's going to make a difference. CCl4, polar or non-polar? Non-polar. Because all four directions are identical. What about sulfur dichloride? Polar. Because despite the way it's drawn there, it's really not linear as I drew it. Those lone pairs deform the shape and make it nonlinear, make it non-symmetrical. This is CCl4. Equal bonding in every direction. But this is sulfur dichloride. 4 locations, not all 4 identical, and therefore polar. Now the thing about polar, if you think about it in terms of electronegativity, chlorine is more electronegative than carbon. All these chlorines are trying to draw electrons away from carbon. But the pull is equal in every direction and they cancel each other out. And so you don't have any charges there. But in this, where the pull is not equal in all 4 directions, you do end up what's called partial charges. It's a little delta negative for the chlorines, delta positive for the sulfur. That just means that the chlorines are more electronegative and they're the ones that are draining out the electrons. That's not symmetrical, and you end up with what's called partial charges.